Hey everyone, this is just a derivation video where we derive the linear and angular equations of motion. So, first of all, we'll start off with our relation between or our time derivative of angular velocity, and that is d omega on dt, which is equivalent to theta dot, theta double dot is equal to alpha, and we'll use separation of variables like so. So d omega equals alpha dt, and therefore if we integrate with respect to time and with respect to the change in angular velocity, we'll end up with an integral like so. This is, of course, assuming constant angular acceleration and assuming that our initial time is 0. So this equation ends up being minus omega naught equals alpha t. That's very similar to our high school equation of linear motion, where we make omega the subject and we end up getting omega equals omega naught plus alpha t. We'll let that be our first equation of motion. Our second equation of motion will involve substitution of this first equation into the time rate of change of angular displacement. So d theta on dt, which is equivalent to theta dot, is equal to omega, where omega is this equation up here, and then we'll use separation of variables again. We'll end up with our angular displacement, so theta naught theta equals 0 to t. Now I've skipped this step in here of separation of variables and gone straight into our integral, just saving a bit of time. So, evaluating our integral, we get theta minus theta naught equals omega t. But, actually I should cross this out and we'll substitute that omega in, so we'll end up with integral 0 to t of omega naught plus alpha t dt. We end up getting omega naught t plus a half alpha t squared, and our equation of motion becomes theta equals theta naught plus omega naught t plus a half alpha t squared, which is very similar to our second equation of linear motion. Now we'll look at the third equation of motion, which is our displacement and angular velocity and angular acceleration without time as a variable. So when we don't know time, we can still find our angular acceleration, angular velocity, and our angular displacement. To do this, we'll use the chain rule. Now, in this case, we know that alpha equals d omega on dt, but d omega on dt, if we decompose that, we can get our change of angular velocity with respect to angle, so d omega d theta multiplied by our angular velocity. So that times d theta on dt, which is simply just omega. So therefore alpha equals d omega on d theta times omega. Now if we apply separation of variables like we have done in every other example, we end up with an integral like so. So the integral becomes theta naught theta of alpha d theta equals integral from omega naught to omega of omega d omega. Now if we evaluate that, we end up getting alpha times the differential, so the difference between our angle at time t and our initial angle, so theta minus theta naught, we end up getting omega squared onto omega naught omega. We evaluate that, we end up getting omega squared minus omega naught squared on 2. And then we'll make omega squared our subject. And we'll end up getting which again is very similar to our third equation of motion. Now, if we change around our, say we change around our theta with length, or we'll let it be, I don't know, we'll let it be x in this case, because if we can prove it for one-dimensional axis, we can prove it for all axes. So if theta, so displacement in angular terms it's theta, but in linear terms, we'll just draw up a separation here. We'll usually use x as our displacement. Now we'll use v and a, so they're our linear velocity and linear acceleration represented by velocity at the v and a, and we've just shown that above that our omega is our angular velocity and alpha is our angular acceleration. So omega and alpha is acceleration. Now, if you go ahead and substitute in x where we had theta, v where we had omega, and a where we had alpha, we'll end up with the same equations of motion, but they represent motion in different reference planes. This is polar motion, or cylindrical, or spherical, or whatever the coordinate system is, and this is linear motion. So in a line in this direction and a line in this direction, we'll end up with actually a line in this direction, line in that direction, and a line out. We'll end up with motion with respect to those three directions. Okay, that's all for this video. I hope you understand a bit more about the derivation of angular velocity. Thanks.